So welcome everyone to the third talk of the Equivariant Elliptic Cohomology Seminar. So today we have Giovanni Rossanigo from University of Regensburg, and he'll be talking about orientations and oriented elliptic curves. So Giovanni, please take it away.
So hello everyone. The goal of this talk is to give an introduction to orientations and oriented elliptic curves. And in order to do so, we have to speak first about group schemes in spectral algebraic geometry. And the way we will do that is that we will straight go with a generalization from the ordinary algebraic geometry case. And then we will talk about orientation, that we have to think, and we have to think about orientation as gadgets that allow us to define equivariant cohomology whenever we have theory. And then hopefully state a classification result when we mix the two things together. So if we mix certain group schemes, elliptic curves, and the theory of orientations. And I would like to start this talk with a warning, because I'm not an expert on elliptic cohomology and I don't work exactly on this field. So if I say something wrong, please correct me. And I will be very happy to learn something from my mistakes. Okay, let's start with derived group schemes. The idea is that last week, or a couple of weeks ago at this point, we have introduced, we have seen as how spectral algebraic geometry can be seen as a way of generalizing ordinary algebraic geometry by building the foundations directly with the language of homotopy theory, so the language of infinity rings. And I would like to recall that whenever we have an infinity ring whenever we have an infinity ring A that we have to think as a commutative algebra object inside the infinity category of spectra equipped with the symmetric monoidal structure given by this match product, we are able to attach to this infinity ring a topological space. We take the prime idea, the set of prime ideas in the underlying commutative ring, and we equip this topological space with a sheaf of E-infinity rings. And the idea is that exactly we mimic what happens in the ordinary case. So when we have a distinguished open subset, so the set of primes that avoids that element, we localize, in the sense of the infinity rings time, the infinity ring A at the element. This equips the space spec of pi naught A with a sheaf of commutative infinity rings. And by definition, we declare this space to be the local gadget of our geometry, so the affine spectral schemes. A spectral scheme, then, is just a topological space equipped with a sheaf of infinity rings that locally looks like the affine geometry. So this is the main gadget that we will use. Later, we will need to consider more general spectral Deligne-Mumford stacks. And I've not written anything here, but we have to consider them like as infinity topos, so like, let's say, the sheaves on some topological space on some site, equipped with a sheaf of a commutative ring spectra that locally looks like the étale spectrum of an infinity ring. I will not enter much into detail. We just know that these things exist and that they generalize the ordinary Deligne-Mumford stacks. Okay, whenever we have a spectral scheme, so we are in the realm of spectral algebraic geometry, what we would like to do is to define ordinary objects. We would like to define analogs of ordinary objects in this realm. And the point is that many times the usual definition that is most straightforward is not the correct one. And for example, think about, we would like to define group schemes. Defining a group schemes in ordinary algebraic geometry is just giving a scheme and a multiplication map on the product of the scheme we set into the scheme, such that it satisfies a bunch of relations. Of course, so used to this is not a good idea when we look at we work with categories, because the amount of coherence condition that we have to specify in order to even define these objects grows immediately and indefinitely, and we have no concrete way of organizing this data from this point of view. So in general, it's useful to look at some other perspective. In the case of commutative group schemes, or in general with objects defined in spectral algebraic geometry, is always useful to look at, to use the Grothendieck factors of point of view. And in this case, given a spectral scheme, X O X, we will define a commutative group scheme over X, or commutative group X scheme, I would prefer to use over X, to be just a functor from the category, the infinity category of spectral schemes over X, to commutative algebra object in spaces. We have to think this as the ordinary analog of the infinite of the category of schemes over X, and this as the category of abelian groups. We will require this functor to be such that the composition with the forgetful functor to spaces is representable. And we will represent it by a scheme G, a spectral scheme G or G. In general, this is not sufficient to give a spectral scheme, a commutative group scheme, in the sense that the theory that this produces is not the best theory imaginable. Indeed, we will add a further condition to be, we will require the representing object to be a flat spectral scheme over XOX. This means that we have a representative object and a map of spectral schemes, just a map of topological spaces, and a map of sheaves of commutative rings on or X, such that whenever we look at open affines in G and X, and with the obvious inclusion relation, the map of commutative rings, the one induced by applying the structural shift, is flat. Flat in the sense of infinity geometry, that is, it is flat on the pi naught, and we have an isomorphism of graded commutative rings. So the idea is that when you have a property of rings, a property of ordinary rings, and you want to extend this property to infinity rings, you just ask the property on the level of the pi naught, and then you lift, and then you ask the gradient commutative rings to behave kind of the same. So when I speak about a commutative group scheme over X, I mean a functor which is represented by some spectral scheme, which is flat on the base. And as I said before, flatness is really something which we have to impose. And the point is in the non-full immersion between schemes and spectral schemes. The idea is that when we have an ordinary scheme XOX, so ordinary scheme, this is a sheaf of commutative rings, we can turn these sheaves of commutative rings into a sheaf of commutative ring spectra by just post-composite it with the Eilenberg-MacLane functor. And after a possible Cauchy-fication, the geometry of this gadget in the sense of infinity rings looked like affine. So it really will construct a spectral scheme. And if one just looks at objects, it seems that there is an inclusion of schemes inside spectral schemes. But spectral schemes are exactly constructed to not get this inclusion fully faithful. The point is that this map is not full in general. And the fullness, it's something maybe related. I always like to see it from the point of view of intersection theory. But the point is that when we look at commutative schemes over a spectral scheme which is obtained by an ordinary scheme, then the notion of group scheme is exactly of that of flat commutative group scheme. And without flatness, what happens is that we are not able to identify this product here. So in general, computing the multiplication map in the case of schemes and spectral schemes without the flatness assumption will produce two different results, something that we don't want. So better to, since this inclusion it's not nice, it's better to look directly at flat objects. So to sum up, we have this definition of commutative group scheme, and the requirement of flatness is just something technical that we can avoid, but remember that it's there. Okay. The next goal is to use commutative group schemes to define equivariant cohomology. And in order to fully motivate why we need the theory of orientations, I would like to start with a very simple question. Suppose that we have an infinity ring, so a cohomology theory. We have a way to assign to each space a collection of cohomology groups, organized in a certain way with certain coherence conditions and so on. And suppose that we are able to construct a commutative group GM over the affine spectrum spec A, so a commutative A group. Can we construct a naive equivariant cohomology theory, let's say an S1 equivariant cohomology theory? The answer is that in general, if we just start with and we have a cohomology theory, one can do a very simple thing. We can look at what's called Borel cohomology. Essentially, this cohomology theory is not that interesting in the sense that when, if you know sufficiently well enough your group, you can construct the space AG, which is the cover of the classifying space BG, and then you can form if G, your group, acts on your space X, the homotopy quotient. And Borel equivariant A cohomology is defined as the A cohomology of this space. In many constructions, this theory is not that interesting. Like for K theory, it's not the right equivariant cohomology theory that we naively expect. The one that classifies vector bundles with an action of G. And for this reason, we try to construct a new cohomology theory, which is S1 equivariant cohomology theory, A cohomology theory. The general theory tells you, the general idea tells you that there should be a comparison map that allows you to that allows you to understand the naive theory with the most simple that you can get from your data. And in the example of K theory, this is exactly what happens. It's possible to construct something which is the S1 equivariant K theory, and this is the representing spectrum, and the Borel equivariant K theory. And there is a map in this way that simply forgets that you are acting with, you're going to the homotopy quotient, so all the vector bundles are already equipped with the J action that you want. And the question is, okay, let's start with an infinity ring, and we have a commutative A group. Can we use this commutative group to construct an A cohomology theory, which is equivariant under some action, some group? And the answer is that is furnished by the theory of orientations. And in order to give the definition, let me recall that the infinitive complex projective space, which is the main tool of the talk, the main object of the talk, has the structure of a commutative algebra object in spaces. There are several ways you can see this. This represents something, but a more handy approach to show that this is indeed a commutative algebra objects is to identify the space with the set and the space C is to construct the multiplication map directly. This is classical. The only thing that one has to pay attention is that this multiplication map has an inverse which is not continuous, but it's homotopy equivalent to something which is continuous, so it all is fine. Okay, the definition of the preorientation is the following. We start with a commutative group scheme over a spectral scheme X. so full generality. So we have a functor, which is representable by some spectral scheme, G O G, which is flat over X. A pre-orientation of G is given by a map of from the infinite complex projective space to the global section of the functor G in commutative algebra object over spaces. And in this case, to pack up the notation, we will refer to a pre-oriented group, X group, or pre-oriented group scheme over X, to be a commutative group scheme over X with the data of a pre-orientation. This is in full generality, and as I said before, we would like to analyze group pre-orientation, or better, we would like to answer this question in the case where the group scheme is over some affine spectrum. So let me consider the case where X is the affine spectrum of an infinity ring. Let us pick a pre-oriented spec A group scheme and assume that the global section are called A of S1. This will be the representing object of the naive S1 equivariant A cohomology theory. In the case of theory, we will see that it is possible to identify the space with the K theory of G equivariant, the G equivariant K theory, essentially. Whenever we have an X valued point of G, by definition, we produce a map of spectral commutative ring spectra from the global section to A. And this map, we have a lot of these maps, and they are all they are parameterized by the data of the pre-orientation. So we get one of these maps for each point of CP infinity. In particular, what we get by adding the data of a pre-orientation to the commutative group scheme G is a map from the global section to the cotensor of A over CP infinity. And this is the comparison map I was talking about before. We have to think of the left-hand side as the naive cohomology theory. And this one, the right-hand side, as the Borel equivariant cohomology theory. Okay, this is the data that a pre-orientation gives. How to construct them? The idea is that there is no real geometry involved here, so we have just a bunch of definitions. And the interpretation is that I would like to furnish is that it is possible to interpret pre-orientation as elements in a particular homotopy group. And the idea is that if we think CP infinity as the space of polynomial functions over C, which are not zero, and we identify the space by the proportional relation, then we can think about every CPN inside CP infinity as corresponding modulo scaling. So the quotient that the subspace of polynomials of degree less or equal than n. In particular, CP0 is the class of the unit. And since we have the fundamental theorem of algebra, every polynomial in CX factor as a product of linear factors. In particular, at the level of geometry, it implies that CP infinity is generated by CP1 as an abelian group. Modulo one only relation, which is the one that requires the point to be the unit. So the idea is that we can think CP infinity as a commutative algebra object in spaces, and the structure of commutative algebra is exactly given by this identification. It is generated by a line with the only relation that we fix what the unit is. In particular, giving an orientation, so giving a commutative algebra object in spaces between CP infinity and the global section of our group scheme, is something that is completely determined whenever we fix a point from a map from the two sphere to the global section, modulo the relation that we have to send the base point to the identity element. It has to be a map of commutative algebra objects. This, if you accept this as a proof, we have shown that whenever we have a spectral scheme and a commutative group scheme over the spectral scheme X, so a flat scheme over X, then we have a bijection between the pre-orientations of G and the elements of the pi2 of Gx. This is exactly specified by this data here. So sorry. Okay. Now, as simple as it might be, this is actually not completely what we want. In the sense, we have said that in order to compare Borel equivariant cohomology with the naive cohomology, naive equivariant cohomology, we can add the datum of a pre-orientation, because it gives us the structure of, it gives us a map of commutative algebra object from some spectrum that we interpret as the global, as the spectrum representing naive equivariant cohomology theory, to the spectrum representing Borel cohomology theory. The point is that we will, examples tells us that this is not exactly what happens, in the sense that in general there are two maps of this type, and there is always one map which is there, but it has not to induce a pre-orientation. For example, the zero element always of pi2 Gx always induces a pre-orientation of G, and we don't want this pre-orientation. It's in some sense the trivial orientation doesn't tell you anything about the geometry about the problem. So we would like to get rid of this pre-orientation, has to disappear. So we have to impose conditions, and it is useful to look at what happens with complex K field. As we said before, we have a way to construct a map between naive cohomology, equivariant cohomology theory and Borel equivariant cohomology theory. This KS1 can, I would like to not enter too much into detail, but this KS1 can be seen as a ring of functions of some commutative K group, which is the commutative K group obtained by looking at the spectrum as an ordinary scheme of this polynomial algebra. And what is so special about the example of K theory is that this map exhibits the Borel equivariant cohomology as the ring of formal function on the scheme, on the commutative K group GM near the identity section. So what we have to imagine is that we have the spectrum of this polynomial algebra, and near the identity section, the comparison map between naive cohomology theory and Borel cohomology theory exhibits the ring of formal functions. When I learned this, I was kind of like scared about it, but it seems totally natural to be the case. And whenever we have an orientation, a pre-orientation, sorry, this pre-orientation gives some map between the formal scheme over this KCP infinity to GM. And this map exhibits the left-hand side as the formal completion of GM. So this is maybe to be compared with what we said in talk 1. And this is the condition we are looking for. Not every the zero element of pi2 Gx will not induces a preorientation, but this preorientation does not have this property. And in order to formalize the fact that the naive the Borel cohomology, equivariant cohomology theory exhibits the ring of formal functions, or the formal completion of the group scheme that we are looking for. We need to work with scalar differentials. For example, in this case, it happens that induces exhibit the left-hand side as the formal completion of the right-hand side, just because we are working with one-dimensional formal groups. And the derivative of this map, ds, over, let's say, dx, which is the variable of this formal group, is invertible, which is a notion, which is something related to the study of scalar differentials. In the more general case, this condition can be built by looking at the pullback of scalar differentials. So the picture is the following. We have an infinity ring A, and we have a commutative group scheme over A. To every commutative group scheme, we can assign, to every spectral scheme, we can assign an underlying scheme just by taking the pi naught of the structural sheaf. So taking the pi naught, we produce a map of ordinary schemes from the affine spectrum over pi naught A and the scheme pi naught G. We can then take the sheaf of differentials on pi naught G and use this map to pull it back to spec pi naught A. And let's say that we have that the sheaf, that this pullback sheaf is called omega. When we look, we are interested in studying the global section of the schemes. So, the global section omega tilde over spec pi naught A of A. In the case where G has a preorientation, so we have a map, we have said this should be a map from CP infinity to our to the global section of our group scheme, which by the lemma before we can interpret as an element of the pi 2, so an element from the sphere S2 to the global section. What we can do is looking at an open affine that contains the identity section of the structural sheaf over G, over the G spec. In this case, the map sigma, our preorientation, determines a map from S2 to the space of commutative algebra objects, of space of maps of commutative algebra objects between B and A. And by adjunction, or by remembering that commutative algebra objects are cotensored over spaces, this map is actually determined once we specify a map of commutative algebra objects with the global section over U, so B, to the cotensor of S2 with A. And a simple calculation with connected components show that this map produces this sigma, the choice of this preorientation, produces a map from pi naught B to the direct sum of pi naught A with the second homotopy group of the ring, infinite ring A. And this map is a map of pi naught A algebras. This is quite a long computation, I have to say, especially this isomorphism. But if someone has a way of computing very fast, I will be happy to do it. And what happens is that this map can be identified by a map of commutative rings when we project to the first component. And this map of commutative rings corresponds to the identity section of the group scheme G. And when we project to the second component, we construct a pi naught A algebra derivation of pi naught B into pi 2A. And this is exactly the map we are looking for. By some map, what we see is that this pi naught sigma classifies a map beta between the global section of the sheaf omega, so the structural, the pullback of the sheaf of Kähler differentials, and pi 2 of A. And this is what is the condition that we were looking for. This allows us to ask the S of the X is invertible. So we can exclude the trivial preorientation. So we will say that given a commutative, an A-infinity ring spectrum A and a commutative group scheme over the affine spec of A, and given a preorientation which we represent as an element of the pi 2 of the global section of the group scheme, we say that this preorientation is actually orientable if the map, the induced map is smooth of relative dimension 1. So this map is smooth and every fiber has dimension 1. Over every fiber which is non-empty, at least. And the map we have classified via the procedure before induces an isomorphism between the tensor product of the n homotopy group over pi naught of A with the global section of the Kähler differentials and a shift by 2 of the n homotopy group. And I would like to express that this condition is actually very natural once you do all the computations, which are very long and like you have to do it by yourself in order to see that it makes sense. Okay, when we have, when the preorientation sigma is orientable, we will just say that an oriented A group, a preoriented A group is just oriented. And look that the map beta, it's part of the data that we have to give, something that we have to prove that it's there. When we have a preoriented X group, we can, okay, this was the local definition. In order to globalize to general objects, we will ask the global definition, the local definition, the conditional locally. So when we have a preoriented X group, and we know that the restriction to every affine is an oriented A group, then we will simply speak about oriented X groups. Sorry. Okay, in order to, in the first talk, we have introduced what are weakly periodic and weakly periodic cohomologies. And what I would like to say is that, in general, being weakly periodic, it's a condition that we need to ask in order for a cohomology theory to be orientable. So not every cohomology theory will be orientable. So the comparison map, it exists not every time. And the result is the following. If we have an A-infinity ring A, and we have a commutative group scheme over A and a preorientation, if we know a priori that the underlying map, that the map between the underlying schemes is smooth of relative dimension 1, so something has to be there. Then we know that in the case where G is an oriented A group, A has to be weakly periodic. And let me recall that this means that whenever we tensor the nth homotopy group with the second homotopy group, and we go to the n+2 homotopy group, this map is an isomorphism. This happens for K theory, essentially. So we know one direction. Whenever we have oriented A groups, we know that the cohomology theory that we want to use has to be weakly periodic. And if we have a weakly periodic cohomology theory, then one can construct a map beta, which is from the, it goes global section of the pullback of the sheaf of Keller differentials, 2π2, and this map is an isomorphism. So a posteriori, what happens is that we will not be able to construct orientations if the ring spectrum A is not weakly periodic. And the proof essentially follows by looking at this diagram. You need to use all the assumptions, in particular also the flatness assumption, in order to see that one map is an isomorphism if it is the other. And this concludes to say about orientation. So the catch-up from orientation is that they are a way, a data that we can furnish to a cohomology theory in order to show that there is a comparison map between the naive equivariant S1 equivariant cohomology theory and the Borel equivariant cohomology theory. I'm going fast than expected. So if there are any questions, I will be very happy. Otherwise, later. Okay. Sorry. Now we have A group schemes. So flat, we have functors which are represented by flat schemes. And these functors factors over commutative algebra objects. And with A group schemes, we can introduce elliptic curves. Whenever we have an infinity ring A, with an elliptic curve over A will be a commutative A group E over spec of A, such that, and the principle of asking things on a pi naught, it comes again, the map of underlying schemes, pi naught E to spec of pi naught of A, is an elliptic curve. Remember that we are asking flatness. So when we look at this map of underlying schemes will be flat.
Giovanni, quick question. So elliptic curve in sense of like the classical sense, right?
Yes.
Maybe you should say a few words about that, maybe.
Elliptic curve in classical algebraic geometry. Okay, I will say something. Let me skip the first remark. Let's go to the second and then go back to the first one. Okay, we have to imagine an elliptic curve as a commutative A group, or the A group, which is essentially one-dimensional. And in the case of ordinary algebraic geometry, what happens is that we would like an elliptic curve is a scheme with the structure of a one-dimensional schemes over spec of A, which has of a group scheme. And in classical algebraic geometry, what happens is that if you just specify the base point, so if you just give a section of the structural map, then E acquires the structure. The structure of group, the group structure is completely determined. And this is, for example, very specific to classical algebraic geometry. It does not happen in geometry, in infinity geometry, because as always, there is a lot of data that you need to specify. You have to specify all the coherence conditions. And these coherence conditions are not for free. So it's different. Think that it's different to give a elliptic curve in the sense of infinity geometry. Let me just stress that if our ring, infinity ring, happens to be classical, so it's the Eilenberg-MacLane spectrum of a commutative ring, then the two definitions are actually the same. So elliptic curves over the infinity ring HK in the sense of definition are exactly ordinary elliptic curves.
Sorry, may I ask a question?
Yes.
Is it easy to see why if I have an elliptic curve over K, I will get this commutative group, commutative HK group?
You're asking for the, let's say that we start with an ordinary elliptic curve over K. Can I see that it's
because there's a priori a lot more information in that, right? Than just
but this information is actually contained. You do not need to specify this information because you're working on something which is ordinary. So when you look at the case, when you construct the functor G, let me go back a little bit to was really far behind. Okay, when you constructed the commutative group scheme, this functor is actually really easy to produce. You can just start with the ordinary functor. I don't know, I never tried the computations, but I guess it's not that complex to do.
Okay, thanks.
Okay, let me go back. So, the final result of the talk depends strongly on what we did last time. So, last time we looked at this diagram. And the goal was to construct, to show the existence and uniqueness of the universal elliptic cohomology theory. And we have showed that whenever we look at the ordinary étale topos of elliptic curves over of elliptic curves, then it was possible to fill this diagram with a sheaf of A infinity rings that we have called the sheaf of derivation over M. And the main result that I will not prove because the construction is, the proof is very long and, let's say, convoluted, is due to independently Lurie and Hopkins, Miller's, Gors, Hopkins, and Miller. And it says that if we look at the étale topos of elliptic curves with the structural sheaf constructed the last time, then whenever we have an infinite ring, we can produce an equivalence, an homotopy equivalence between the classifying space of the infinity category of oriented elliptic curves, and oriented is really necessary, and the maps between spec A and the topos, these topos. The maps here are computed in connective Deligne-Mumford spectral stacks. So things that generalizes spectral schemes by requiring the object to locally resemble the étale topology. And what's really hard to prove in this theorem is that the classifying space of oriented elliptic curves over A is not representable in the sense it's really actually easy to prove that it's representable. The point is prove that it's representable by the ordinary stack of elliptic curves. And the construction uses a lot the existence of the existence of orientations in order to show that are not asking really something new. But the proof is very long and complicated. You can find it, for example, on a survey of elliptic cohomology. I would like not to go into details. And even with 9 minutes before, I would like to finish my talk here. So thank you.
Let's thank our speaker. So do we have any questions? If not, let's thank our speaker again, and we'll probably stop the recording.